So this next presentation is not my work at all. This is the work of Dunya, Bing, Dmitry, Mateusz, and Yuri. And this presentation is going to be on the joint matrix extension they've been working on in SYCL for quite some time as a way to provide a portable abstraction for accessing the type of tensor cores or matrix multiplication acceleration that's available on almost everyone's hardware today. Yeah. So, as we've all heard, AI is apparently become super important and everyone is obsessed with it. And there's no one way to do it. There are many different levels of abstraction for different types of people. For some people, they only want to interact with things like AI frameworks like PyTorch or TensorFlow. That's their abstraction. Other people are lower level and may want to interact with optimized vendor libraries like cuDNN or OneDNN or PortDNN from CodePlay. But still, then other people actually want to be able to write libraries like that and need to be able to get access to the low-level hardware and potentially, even write things like inline assembly or things like that. So it's important to be able to provide kind of the right abstraction for the right layer. And when you're coming up with these abstractions, there's going to be trade-offs between kind of increasing the level of abstraction versus the amount of control you give the programmer. So joint matrix is an abstraction designed to kind of sit in the middle. It's not the lowest level thing, but it's kind of a step above those as a way to abstract common functionality amongst different implementations of these kind of low-level tensor cores. So the joint matrix extension in particular, we think is useful for kind of most of the GPUs out there. Our implementation today can target the Intel GPUs like Ponte Vecchio or the NVIDIA tensor cores, but it also is able to target things like the advanced matrix extensions on the Intel Xeon CPUs. So we think it's nice because it can improve programmer productivity. Now we've slightly raised the level of abstraction, but ideally still exposing a reasonable amount of performance for the programmer. And ideally, it's the implementation of joint matrix that's going to kind of map very nicely to these low-level intrinsics to access these tensor cores. So the current status of this is that it is a feature that we've implemented. It has been available for over a year now, and we're still working on it to improve the functionality and improve the performance. And while it is there and while it's giving good results, it's important to note that it doesn't completely solve the problem. You can't just insert joint matrix into your code and get kind of the best performance on all the different types of hardware you may be trying to target. It's simply a tool that you can use, but it's still ultimately up to the application programmers to then kind of use it in the right way. So different hardware will require often kind of different tiling factors or different matrix sizes are supported on this device versus that device in order to really kind of get the best performance out of it. So the outline of this talk is going to be a quick introduction to the matrix units available on Intel hardware. So AMX on Sapphire Rapids and XMX on PVC. Then we'll go into a brief overview of what the joint matrix itself looks like and what it can do. And then we'll talk a bit about how you can do this type of tuning in your applications and the features of joint matrix to help that, which include things like the matrix query interface to tell you what are the sizes and types that are available in your tensor core on your hardware. So moving on to hardware. So PVC, we've seen a lot of slides about it because we have a lot of fine folks from Argonne here. But the point being is it's a pretty big GPU with a bunch of different tiles and a bunch of different cores, and all of these cores have a matrix engine. So this has the ability to do a lot of gems really fast. And Also, it's not just GPUs that have these things now as well. A lot of CPUs are starting to have this. I believe ARM has an extension for it in the ARM ISA. We have the AMX in x86. And what this did really was just add a little matrix accelerator beside the core. And it extended the register file with these kind of 2D tile registers. And the way you program this thing is kind of a very simple, risky style instruction sequence. You have kind of intrinsics to load data into your tiles, store data from your tiles back to memory, and then do your matrix multiply. So next we'll get into the nuts and bolts of the joint matrix extension. So it's actually a pretty small thing. There aren't too many pieces to it. So it's currently an experimental extension, which is why it's in a very long namespace in DPC++. And the main thing is just the joint matrix type itself, which is a templated type that has a lot of different template arguments, mostly about the types of data for the result and inputs, how you're going to use the matrix, because it helps the compiler a lot to know if this is the first matrix or the second matrix or the accumulation. And then things like how many rows does your matrix have, how many columns, and what's the layout of it. Because it turns out everyone loves to have weird layouts for their matrices. A thing that's very important to note about this is the word joint. Similar to a lot of the group algorithms in SYCL 2020, the word joint there signals that this isn't something that's performed by a single work item inside a work group. This is an operation that's meant to be performed by multiple work items working together or jointly to compute an answer. So the first template argument of the joint matrix class is a group. So it could be a work group, it could be a subgroup, because that's what we have in SYCL 2020. Or in the future, it could be any of the groups I mentioned in the last talk. There are a couple enums that are useful when defining these things. The first is this use I mentioned. So is it the first matrix, is it the second matrix, or is it your accumulator? And then layout is important. Is it row major, column major, dynamic, or potentially other options? So once you've declared your joint matrix objects, then we've defined a few operations that you can use them with. The first couple are basically how do you get data into your joint matrix? We have a fill operation that just shoves a value into all the locations in it. And then, of course, we have a joint matrix load that will load some data from memory and put it in the joint matrix in the correct layout. And then since we have a load, we also have a store. And the whole point of joint matrix is to do optimized matrix multiplication. So the main operation here is our MAD. So our multiply and add function. And that will take a group argument and several matrices. Our result, and then your matrices A and B that you're going to multiply, and potentially a matrix C to accumulate. So that's where we started, but we found there were a couple other useful things to add as well. The first is a function we call joint matrix apply. And that exists to perform element-wise operations on your matrices. Because if you're coding machine learning algorithms, often there's this notion of either pre or post ops, where you may want to, multiply every element in your matrix by a scalar, or do something like a ReLU or some activation function. And joint matrix apply is our mechanism to do that. And then we also have a copy, which can be useful. And one of the things you can do with copy is actually you can use that to change the layout of a matrix. Because sometimes you may kind of chain together multiple matrices and want to use them in different ways. Okay, So we have a example here of how you can use this. It's a bit dense, so I won't say it's simple, but it has a few kind of key pieces. So we have some boilerplate at the top defining our ranges of everything. We're going to allocate some memory to represent our A matrix and B matrix, and we're going to use USM for that. And we're going to allocate some memory for our C matrix, and then submit a kernel to do some matrix multiplications. So one thing that's important to note about the joint matrix load and store functions is that they don't really work on generic pointers today due to some limitations in how some of these tensor cores work. So they actually do need pointers that have memory space annotations. So that's why the first thing we do here is do an address space cast of these kind of generic pointers to let the runtime and compiler know that no, this is really a global pointer. So that's an important thing. And then we get inside our kernel. And in this case, we're going to be operating on kind of subgroup level joint matrices. So a subgroup is all going to cooperate together to do some matrix multiplication. So we're going to get a handle to our subgroup, create some joint matrices. So in this case, these are going to be subgroup level joint matrices. Our data type is going to be B float 16. The first one is going to be our A matrix. The second one's going to be our B matrix. Our A matrix is going to be M by K, and it's going to be row major. And our B matrix is going to be K by N, and also row major. Next, we'll declare our accumulator, our C matrix, which is going to be of type float. So our data type there is wider than our input matrices because we all like to be numerically stable. And this is an M by N matrix. And we'll then begin by just initializing our C matrix to 0 using joint matrix fill. And then we'll have basically a loop over K. And inside this loop, we'll load a bit of matrix A, we'll load into matrix B, and then we'll perform our multiplication. Then at the end, we're going to do one of these little post-ops. So on every element of C, we'll do this ReLU function, and then we'll take that result and store it back out. Yeah, so like I mentioned before, we've been shipping this for about a year or so. The current implementation works on Intel CPUs, GPUs, and NVIDIA GPUs. And of course, between these three different implementations, they don't all support the same parameter types for everything. And we'll get into the kind of the different parameter types that are supported on these in a second, but we'll next have a brief digression into comparing SYCL joint matrix to the approach of other programming models. So in particular, joint matrix is designed to be pretty similar to what a lot of other programming models show. So CUDA has a way to give access to the tensor core. And then there's extensions in a lot of the other Khronos models as well, basically kind of WMMA style matrix multiplication. So CUDA has something very similar. The only major difference between what joint matrix supports and what CUDA supports is how you deal with element-wise operations. So joint matrix has this joint matrix apply, and in CUDA for the element-wise parts, they have this notion of fragments. And fragments are kind of interesting because they give you a handle to the data, and then you can just do things on them. But what they don't have is they don't tell you which element, for every element in a fragment, they don't tell you which element of the matrix it actually is. It's kind of it's not something that's defined in the spec. So you have to be very careful with what you actually do with them. But otherwise, they're meant to be pretty interoperable, which is how we're able to implement joint matrix on top of the NVIDIA backend. We do have kind of a few device-specific extensions on top of this. So I just mentioned that with fragments in CUDA WMA, you don't have any notion of which matrix element a particular piece of the fragment is. On the Intel device, we do have that. So we have an additional form of joint matrix supply that takes coordinates that can basically define the mapping inside your matrix, so you can get a handle to a specific matrix element and then do something with it, which can be useful for certain things. Good. So next we'll get into the query interface, which is a very important thing to be able to actually use this correctly and efficiently on your hardware. So we'll go into some various supported combinations on the 3 types of hardware I mentioned. So on the Xeon CPUs, we support basically 2 combinations. For matrix A and B, it can be an int 8, either signed or unsigned. And your accumulator type is going to be int 32. And we support M's and N's up to 16 and K's up to 64. And then the other type that's supported is your input matrices are B float 16 and your accumulator is a float with very similar sizes, but a little smaller K because our data types are twice as big. The GPU is pretty similar, but it supports a few new types as well. We support FP16 there as well as TF32. And the sizes are a bit different. The Tensor Core, of course, supports on the NVIDIA GPU, supports the biggest number of options. And this is probably for A100, I think H100 and B100 support even more. So how do you actually get this out of the interface? Well, we have a query that is a device query we added this SYCL that basically gives you back a vector of all the possible combinations. So we have this combination struct with all these different fields telling you, what's your maximum M size, N size, K size, and what data types do you support for the different matrices. So you can call this and get this vector back and then figure out all the different combinations and use that to tune for performance. Yeah. So depending on the device, you may want to handle things very differently. On some devices, you may want to kind of process your M and N dimensions in parallel and sequentialize your K loop. So like in the previous example, inside our kernel, we just had a loop over K. But on different devices, you may want to interchange your loops in different ways. But a key thing is, so these types tended to be very constrained, but when people talk about doing matrix multiplication, they often talk about multiplying far larger matrices, like 4K by 4K or 8K by 8K or even larger. So if that's what you're actually trying to solve, then classical performance optimizations and compiler optimizations come to the rescue. You can't have a talk in computer science without mentioning tiling. So in order to get the best results, you really need to be aware of the characteristics of your hardware, how big your cache is, what sizes of matrices are supported, how many registers do you have, and pretty much tile along every dimension and potentially have different tile sizes depending on different hardware. And that's where the query comes in. And that's really the takeaway from this. So we'll wrap up now and just summarize that the joint matrix extension is here, and we have preliminary implementations on multiple hardware types. I think support for AMD is improving as well. But this is really kind of part of a larger ecosystem. So we've defined this in SYCL, but in order to make it work everywhere, of course, that means we also have an extension for SPIR-V. SPIR-V has its own extension, and we have kind of a small extension on top of that for some extra pieces. There's also been work from the University of Illinois and other places to try to add the notion of matrix types to LLVM-IR, although I think that's still in kind of the preliminary phases. So as we continue to develop this, we're trying to write a lot of codes using it so we can check it out, its performance, and figure out how it can be effectively integrated into SYCL machine learning codes, either for, LLMs or integration into things like PyTorch and TensorFlow. And ideally, we'd like to continue to develop this to a point where we turn it into a potential KHR extension that could maybe one day find its way into a future SYCL spec. So, thank you.
So the joint matrix type is variables of the joint matrix type. They kind of are like an interesting position between private and local memory, right? Because they like look like they should be registers, but actually they are kind of distributed between work items.
Exactly.
So how, like, is there an easy path to implement this on a host-only implementation?
Oh, that is a good question. So one of the discussions we had in the early days of this was something that had been kicking around previously is like, does SYCL need some notion of kind of subgroup local memory? Like, is local memory too coarse-grained? And that's maybe something that as we try to think about generalizing the concept of these groups, maybe we need to define a group concept that has kind of group local memory. And you could define different levels of this, and that could be a way to try to address it.
Yeah, I mean, this also appears in, like, if you have subgroup shuffle operations, this is all, I mean, it's only used within the function call, but still it does something that's similar to a subgroup local operation, right? Okay. And then on this, on the slide where you compared the SYCL version to CUDA, you had the CUDA version had a loop over every element in the matrix, I think. Like on the right, you have a loop, but that loop is executed in every work item, right? So would that mean that every work item has access to the entire matrix?
Are you talking about the red loop at the bottom?
Yeah, red loop, yeah.
Yeah, so that's over the fragment. And the fragments are a little weird.
So they basically just have whatever the one thread is actually owning from the okay.
Yeah.
Okay, I get it. So num elements is not the number of elements in the matrix.
Exactly.
Even though it
the
has
number
matrix
of
num elements, but
fragment.
it's weird. Okay, get it.
Can I think of this SYCL extension as primarily maybe built on top of the SPIR-V cooperative matrix extension?
Exactly.
Okay. And second question is more on the AMD. Is it mostly a work in progress on your side to kind of test out the AMD with the ROCm RDNA stuff?
Yeah, I think, we started developing on the Intel and NVIDIA devices, and then I believe CodePlay actually is driving the implementation on AMD. So that's probably a question for Hugh.
Okay, got it. Thanks.
I thought I caught it on one of your slides, but then it switched real quick. Was there like a joint matrix gem that tries to do all that in like one call?
Oh, no.
Oh, I thought I saw it.
Yeah, no, it's just the different pieces that you kind of have to assemble them in the right order to be useful. Yeah, if you had something like a joint matrix gem at that level, that's basically calling a blast library at that point.
Yes, the file system is supported with films or whatever. Some vendors these methods. Operation still have to say 16-bit.
Yeah, exactly. Like on AMD, I believe they support FP64 in their Tensor Core. Yeah, and then on Blackwell, it was just announced, the major focus is on FP4.
I know on the AMD side, there is also support for sparse tensor operations or sparse matrix operations. Does this SYCL one also support sort of the sparse or?
Potentially in the future, but today is just dense.
Okay.